So it's a pleasure to introduce the last speaker of this afternoon session. Is Massimo Frittelli from Università del Salento, and is going to talk about the virtual element method for bulk surface reaction diffusion system with an application in electrochemical.
Okay,
thank you very much, Massimo, and the floor is yours.
Thank you for the kind introduction and for the invitation. So this is a joint work with Anotida from University of Sussex and with Yvonne from Università del Salento, and it's extracted both from published and unpublished work. So this is the theme. We consider the so-called bulk surface PDEs. A bulk surface PDEs is basically a PDE in a bulk domain omega coupled with another PDE whose domain is the boundary of omega. So we have a bulk PDE coupled with a surface PDE through arbitrary, possibly nonlinear boundary condition. And this is a class of PDEs that is quickly growing in the literature because such complex geometries easily lend themselves to a wide range of applications. What we want to do is try to exploit the nice properties of virtual elements in the context of bulk surface PDEs. So let me start by introducing more precisely what bulk surface PDEs are with some notation. So we refer to the bulk domain omega, we call it bulk, and it's a set in R2 on R3. So we consider two different space dimensionality. And we refer to the boundary of such domain as the surface, even if in the case d equals 2, it is a curve actually. But in the language of bulk surface PDEs, we call it the surface nonetheless. And we are going to use this notation. Nabla gamma is the tangential gradient operator on gamma, and delta gamma is the Laplace-Beltrami operator. So we are going to consider two PDE problems. Elliptic problem, which is this one, in which you have basically a Poisson equation in the bulk coupled with another linear equation on the surface. And these two equations are coupled through linear boundary conditions. As you can see, such model was applied to, was used in this reference, and it has several applications. But more importantly, we consider parabolic bulk surface PDEs, such as this one. We have this semi-linear reaction diffusion equation in the bulk, coupled with another semi-linear reaction diffusion equation posed on the surface, and the two equations are coupled through nonlinear boundary conditions of Neumann type. And as you can see below, these are two of many possible applications that exist in the literature. So we are now ready to introduce the virtual element for the such bulk surface PDEs. In the case d equals 2, the method and its analysis was published in Numerische Mathematik this year, and the case d equals 3 that I'm going to present as well is work in progress. So what is the background of bulk surface PDEs? Well, if I have my bulk surface domain, through standard bulk surface finite element of triangular type, what do they do in the literature? They basically approximate the bulk with triangles, and such a bulk mesh naturally induces a surface mesh, which is made of lines in this case, as you can see, red straight lines. In the case d equals 3, in the bulk you have tetrahedra and triangles on the surface. What do we want to do instead? We want to take arbitrary polygons in the bulk, and we have still lines on the surface. While in the case d equals 3, we have arbitrary polyhedra in the bulk and arbitrary polygons on the surface. I'm going to be very quick on this part because many of you have already introduced the virtual element space. So I'm just going to recall that we use the enhanced virtual element space. So we start from a 2D polygons. 2D polygon, we introduce this preliminary space made up of H1 function whose Laplacian is a P1 polynomial and whose restriction to the edges is a P1 polynomial on each edge. Then we introduce the usual pi-nabla projection operator inside, and then with this projection in hand, we can define the famous enhanced local VEM space on the polygon. Now that we have defined the 2D space, we can use that to recursively define the space in 3D. So we take each face of the polyhedron, we take virtual element space on each face, and we use that to construct the space inside with basically the same procedure. So this is how the enhanced virtual element space in 2D and 3D is defined. Now, how do we fit bulk and surface together? Well, in the bulk, we consider virtual element both in the 2-dimensional and the 3-dimensional case. Well, on the surface, we have to do a bit of a distinction because in 2-dimensional case, well, we have lines on the surface, so we just pick the 1-dimensional finite element space on the surface, while in the 3-dimensional case, the surface is a 2-dimensional manifold. So in that case, we need virtual elements on the surface as well. But in both cases, the surface space is the trace of the bulk space. So we have this nice property that fits these two spaces together. Well, more standard ingredients of the virtual element gospel, we use the usual Dophy stabilization term, or carpet stabilization if you prefer. We use that to define both the element-wise mass term and element-wise stiffness term. Again, standard definitions, so I'm going to skip through. And the final ingredient that we're going to need is the interpolant operator. Again, we need to distinguish the cases where we have 1-dimensional elements, that's to say lines, or polygons or polyhedra. But in both cases, the interpolant of a given function is the finite element or the virtual element function that agrees with the given function on the nodal points, on the vertices. We are taking linear virtual elements, so the only degrees of freedom that we have are the nodal values. So it's as simple as it gets. So now let's recall our linear problem, and we are ready to carry out a discretization of this problem. So the weak formulation can be carried out as usual. In fact, the Green's formula, there is a Green's formula on surfaces as well, which reads exactly as the standard Green formula. So we get this kind of weak formulation, and this is how the discrete formulation reads. So look at this. The 2-dimensional integrals are replaced by the bilinear forms in the virtual element framework that I've recalled before. But the 1-dimensional integral, well, they don't need to be approximated because finite element functions in 1D are known in closed form. So we can compute this integral without need to introduce further approximate bilinear forms. But if we move to the case d equals 3, this is how the problem becomes. We need both approximate bilinear forms in 2D and 3D. So in the 3-dimensional bulk, we take the virtual elements bilinear forms in 3D. while the two-dimensional integrals are approximated through the two-dimensional virtual elements bilinear form. Notice that in the first equation, which is the bulk equation, a surface integral appears. This is the effect of boundary conditions. So this is the terms that actually couples the bulk equation with the surface equation. I'm not going to present the discretization of the parabolic problem because there are some technicalities, but it works very similarly. So this is I think, the most interesting part from a theoretical point of view, because there are some novel techniques, I think, that we are introducing. So first, how do we estimate errors? Look at this. The surface gamma is the domain of a PDE, right? Of a surface PDE. But when we approximate gamma, we have a set of straight lines. So if you look at the picture on the left, we have this horizontal black line that approximate a portion of gamma. What does that mean? That the numerical solution and the exact solution live on different domains. So when we want to estimate the error, the difference, we cannot write V minus capital V because they live on different domains. So we use the so-called lifting operator. The lifting operator is nothing more than a mapping between the discrete domain and the exact domain. So this is how it's usually done in the context of surface PDE. We write the difference between the exact solution and the lifting of the numerical solution. But because the surface variable is estimated via lifting, we need the same kind of approximation for the bulk species. If we move out the context of bulk surface PDEs, one could simply take the intersection between the discrete and the exact domain and estimate the difference between exact and numerical solution on the intersection. We cannot do that, because if we did that, we would neglect a narrow band close to the boundary, which we cannot do because the boundary is itself the domain of our different PDEs. So we care about optimal accuracy close to the boundary. In other words, we wish to carry an error estimate in the bulk in the lifting sense. So that is a challenge that we must account for in the analysis. Another challenge is that such lifting operator does not preserve the regularity class of a function. So if U, the exact solution in the bulk, is H2, so to speak, its lifted counterpart on the discrete domain is no longer H2. So besides lifting, which we need to state the convergence result, we need another operator to compare the exact and numerical solution that does preserve the regularity class. And that's why we use the Sobolev extension. So take this picture on the left. We have a non-convex domain, right? And we have this non-triangular element. As you can see, part of the element is outside the exact domain. What does this mean? That, again, we cannot compare the two solutions on the same domain. None of the two domains contains the other one. So we need to extend, in some sense, one of the two solutions, or the continuous one or the discrete one. We choose to extend the continuous solution, which is the one with all the regularity that we need. So we have this nice Sobolev extension theorem. So if a function U is of class WMP, Sobolev space, there exists an extension U tilde defined on the whole space R2 that is still WMP, whose restriction on omega coincides with the given function and has the same norm up to a multiplicative constant. So that is another kind of extension besides the lifting that we are going to use in the analysis. And yeah, we can finally state the convergence theorem for the parabolic problem, right? So this is the parabolic problem, and without going through the discrete formulation, I'm going to state right away the convergence theorem. So in the case, in the two-dimensional case, this result is published. In the three-dimensional case is work in progress. So basically we have optimal convergence, that's to say quadratic in space for both the bulk and the surface PDE, the bulk and the surface PDE, that's correct. And this constant C depends as usual on the H2 norm of the exact solution, both in the bulk and on the surface. And it also depends on this H2 plus delta norm of the exact solution in the bulk. This is not optimal. Usually convergence estimates for linear finite elements or virtual elements only depend on H2 norms. In this case, we need this slight additional regularity, which is delta equals 1/4 in the two-dimensional case and 3/4 in the three-dimensional case. But the good news is that we need this additional regularity only in the simultaneous presence of curved boundaries and non-simplicial elements close to the boundary. Otherwise, if we don't have a curved boundary, or if all the elements close to the boundary are triangular, our analysis is happy with H2 exact solution. Let me underline once again that the reason why we need such additional regularity is because we wish to carry out a error estimate in the lifting sense. So that is the challenge that we had to overcome. So why do we need polygonal meshes in bulk surface PDEs? Well, one reason might be the following one. So take a circular bulk surface domain and take a bounding box. Split this box into equal squares, remove the squares that are outside the domain, and take the squares that intersect the boundary and cut those squares. You end up with this kind of mesh. Why is this mesh so nice? Because besides the purple elements, the green elements are all equal to each other. So when you assemble the stiffness matrix, so to speak, you have to compute the square local, the local matrix of the square only once. And then you have compute element-wise matrices only for the purple elements. That's a reduction from n square matrices to n matrices to compute, when n is the number of overall nodes. So computational advantage in the construction of the stiffness matrix. If you go to the three-dimensional case, it's going to be even better, because you have a reduction from cubic complexity to quadratic complexity, so even better. Okay, let me show a numerical example for an elliptic problem. We have an elliptic bulk surface problem with artificial exact solution. So this is what the exact solution looks like. U for the bulk species, V for the surface species. And this is the convergence rate that we observe. Notice that we did not prove anything for the L infinity norm, but experimentally we find that even in L infinity the convergence is optimal. Let me further add on line that this L2 error accounts for both L2 error in the bulk and L2 error on the surface. In fact, it is a tensor product error. Okay, so we have optimal convergence, And let me finally show an application of bulk surface PDEs to electrochemistry. So we have a battery, an electrolytic cell, and as probably most of you know, one of the two electrodes grows due to metal ions accumulating onto it. Okay, right. What one would expect is that if the electrode is smooth, it's going to grow smoothly and uniformly over time. Well, often that is not the case. Spatial structures arise on the electrode, and we observe, for instance, labyrinths, spots, so all these nice structures that you see right here, and even spiral waves. So ordered patterns out of a smooth electrode. That is completely counterintuitive, but that happens in reality and can be described and forecasted through a bulk surface PDE. So in fact, let us consider this model. This is a 2D model in which gamma, the straight line gamma, is our electrode. The green area is the fluid in which the electrode is immersed.
Massimo, 2 minutes. Yeah. You still have 2 minutes.
2 minutes, okay.
Yeah,
enough.
Thank you very much.
Okay, let me skip through the interpretation of the model, but let me go to the, we have two bulk equations, two surface equations, and we have these boundary conditions. So for some reasons, these complicated kinetics describe the model, and this is what happens after some time. Look at the bottom line. The red area is where the electrode is growing in the normal direction. The blue portion of the line is where the electrode is being corroded. In the bulk, red area is where the concentration of the active species is higher. So we have this kind of compensation between the surface growth and concentration in the fluid. Here, I'm going to show a comparison in which electrode growth occurs with or without the effect of the fluid. So what's the difference? We observe experimentally, left plot, that in the coupled bulk surface model, blue line, we have less growth and less corrosion. Right plot, we observe that the chemical composition of the electrode is just shifted up. So this is numerical evidence. And that's all I wanted to say. Thank you for your attention.